Oh, that was me. Okay. I think we got it. Always fun when we're going live. So, hello Cinemeric Nation, and welcome to Simply Cinemeric Live. I am your host, Chris Pollock, and today we're going to be getting into interpolation turning. But before we do that, I want to introduce everybody to my colleague Lars Fowler. Lars is on the line here with us. Lars, say hi to everybody.
Hey, how's everybody doing today?
Perfect. So Lars is going to be monitoring the chat window. So if you guys have any questions that come up, please just fire them into the chat window, and then Lars will either respond directly to you or fire them up to me. But before we go any further, does everything sound good from your end, Lars? Yes? We got? Okay, just checking.
Gotcha.
You never know when I'm on this side of the world. Okay, perfect. So without further ado, why don't we get into interpolation turning? So what do I mean by interpolation turning? Well, basically what it does is it allows us to mimic the tool path that you would traditionally get out of a CNC lathe, but we're going to do it on a 3-axis milling machine. And this is a 3-axis milling machine with no additional rotary axes. So we're going to use the linear axes to mimic this type of tool path. So if we look at it here, I'm going to segue into our up close view. We're going to take a run at it. What we're doing is we're taking a boring bar and we're clocking the boring bar, and then we're revolving around the geometry, and we're only going to spin the spindle 1 full revolution for every 360 degrees of motion. So what is actually happening? So we're just machining a spiral, and in the spiral that's going to be handled by our X and Y axis. There is a Z in feed, so if you look up on the display, you'll notice we have actually 4 axes of motion going. We have our X, Y, and Z are moving, and the spindle is moving. As we start to push down in the Z, that is what mimics the chip load that we would normally define as our feed per rev in the lathe. So if I wanted 10 thou per rev, I would be advancing the Z axis 10 thousandths of an inch downward into the part for every 360 degrees of motion. So why would I want to do an application like this? Well, certainly if I get to scenarios where I have larger parts, maybe deeper bores, bigger bores that are difficult to handle, maybe I can't fixture it in a lathe that's just too large. Certainly I could use a facing head, right? A boring facing head, but they can be quite cumbersome and very expensive. Well, in this application, really all I needed was a standard end mill holder, a boring bar, and to set up this interpolation scenario. So, how does the whole thing work? Well, really, from an application perspective, there's really only one base requirement that I need to be able to do interpolation turning, and that would apply to any CNC, not specifically just the Cinemeric control. And it's the ability of synchronizing or interpolating between my spindle and my axes. I have to have a timing between the two. So there's 2 different types of motion. There's synchronized and non-synchronized motion. So interpolation, when you hear the term interpolation, that means that all the axes are going to achieve or end up at the same position at the same time. So let me show you what I'm talking about. This first move that we're going to do is a non-interpolated move. So here I'm going to move my x-axis and my spindle, but watch the spindle. I command them both on the same line, yet the spindle is achieving that position much quicker than the x-axis is going. This is a non-interpolated move. I'm commanding them both on the same line, but there's no timing, there's no sequence between the two. And for this functionality to work, they both have to achieve the same point in time at the same point in time. So if we take the same program, now I'm going to do something a little different. So this may vary based on how your machine's set up. If you look at the program, my first little example, I was using our S-pause command. Now this specific machine happens to use S-pause in a velocity mode, so it's a non-synchronized mode. A lot of times you'll use that maybe for orient the spindle, for the tool changer, or you can be using an M19. as well. But my machine also happens to be commissioned with the spindle as the SP1 axis. So once I use SP1 as opposed to S-pause, now you're going to see we get an interpolated move. So if you watch, we're achieving the same point at the same time. They're timed together. So this is what we mean by interpolation. So really, step one, or the key step that you're going to need to be able to mimic what we're about to show you in more detail, is the ability of interpolating with your spindle. Once you have that, then it's really a matter of just setting up the tool. So from a setup perspective, it's relatively straightforward. So when I had to define my length, now my machine is set up for gauge line. So my length is going to be set from spindle face to the tip of this boring bar. So I used my Marpros presetter to find that location. But when it came to the edge of the insert, I needed to know an offset from the center of my spindle to the edge of that tool. The other thing I need to do is I need to clock the boring bar. So if I take a look at my spindle, right, I'm going to need to orient or position this to a known location. If I was to run this machine and drive it to my spindle position 0, you notice this is the orientation position if I let S-pause go to 0. So how do I time this so when I'm boring this hole, I can start at 3 o'clock and end at 3 o'clock? I have to apply some form of an offset. So for me, I found that if I use 62.5 degrees, that would set my boring bar normal to my surface. How did I get the number? Well, it's pretty straightforward. In my case, what I ended up doing, I'm just going to reset. When I get out of spindle enable, I use a solid end mill holder, and I am orienting my boring bar with this set screw right here, you see there. So that way, I know that the boring bar is straight to my keys. So I've then just indicated across my two keys until I found that angular position. You don't have to be super accurate here, like setting up a tool in a lathe. You know, I want to be careful that I don't over-rotate, because if I over-rotate too far, I'm going to be rubbing on the bottom side of the insert or even on the seat of the insert. That would not be good. Or if I under-rotate it, then I'm going to be hitting too far up and I'm not going to be engaging my chip breaker properly. So you do want to get it as straight as you can. Now you can't indicate necessarily to the insert itself. This boring bar, if we were to look at it from the front, is a positive raked boring bar. So with it being positive raked, that means that the insert is actually tipped up. If we were to look at it flat, the insert's sitting at an angle. So this allows the chip to drive down and engage its chip breaker properly on the insert. There are also negatively raked tools. In that case, the insert would be rotated down. So don't try to indicate across the insert. You can do the flat or your keys. Now let's say, for argument's sake, your machine doesn't have any ability of now adjusting the offset position. That's okay. You can just time the boring bar, but you would have to hold it in something like a collet. For me, in our control, once I determined that orientation position, I can go into our offsets, and for my active work coordinate, I can now set an angular position for my spindle. And this isn't going to hurt me anywhere else, because if you think about any other applications I would be doing with another tool, once the spindle's in velocity mode, meaning it's just running at a constant RPM for drilling or milling, the fact that there's an angular offset there isn't going to affect me. And that is not going to affect spindle orient in my case. So I can drive this position. The Fryer machine happens to use M19, which is using a different parameter for spindle orient. So I can still drive my tool changer without any adverse effects. So once we've established this position, right, once we've squared up our tool, then I do need to figure out where that cutting edge is in my x-axis. So when I built the tool, we come over to our tool list, I created it as a simple boring bar. So the only way, as the default milling machine goes, for me to adjust my offset was to plug in the diameter of the tool. So if this spindle was spinning and I was able to, let's say, plunge straight into material and went straight down, pulled out, and measured that bore, what would be the final diameter I would achieve at the end, be my diameter of my tool. So obviously I can't do that in this scenario, that's a non-center cutting tool. So what I did was really quite simple. I came over and I set a temporary offset to the edge of my vise. From there, I moved over and I touched that surface. Now obviously if I have a 0 there in X, if I was perfectly on center, the display would be reading 0. But since I was offset, that's giving me the radius of this tool, the distance from the center line to that tool tip. Now in the Cinemeric control, here we happen to have the ability of using, and let me jump to jog, the tool measure diameter manual, and that will just plug that number directly in for me. But even if you don't have this type of cycle, you can just take that number. If your offset table is set up for radius values, you would plug in that radius value of, it was basically a little over a ½ an inch. If you're set up for diameter, I did have to double that value. That gave me the now offset that I needed. From there, really this bar was set up. I had a timing location to start from. I know where the leading edge in Z is, and I know where the cutting edge in X is. So now it becomes, well, how do I create the part program? And the part program is pretty straightforward. So what you're going to do is you're going to create a program that does basically a spiral. Now in my case, I made this a little bit more sophisticated because I didn't want to have 300 arc commands doing all of my spirals. So I really did it all with just 2 and then looped it. So I'll describe that a little bit. But even, if you're going to say, let's say drive this out of a CAM system, which would be a pretty typical scenario for this application, I would then expect to see a whole bunch of G2s or G3s depending on my tool path as I drive down. So what I did was I created just a couple simple variables at the top. I told it what is the diameter that I want to bore. This was set up as an ID turning. So originally I was doing 3.625. Maybe we'll take a little cut. We'll go 3.650. Once I plug in that value, I have, oops, helps if I plug it in the right spot. It's always fun. I have the screen offset for the camera, a little harder for me to see. So I plug in the bore diameter that I want to machine. I have my in-feed amount. That would be basically my feed per rev. So for 360 degrees of motion, I'm going to move, in this case, 5 thou. Then I have my number of revolutions. So that's what, in my case, is going to control the depth I achieve. So basically, my in-feed times my number of revs would give me a ½ an inch overall depth. So you would just make that a factor for however deep you want to go. As far as the program's concerned, pretty straightforward. I do need to get into some starting position. So there I rapided over and I oriented my spindle to now 0. That's going to position my tool at 3 o'clock. Once I'm in position, come down, get to the start, I'm going to feed over to the side of my part, the bore. So in this case, it is my part ID was then feeding into my radius. So my radius value is going to position me over to the side wall. And then I just go into a couple arcs, defining the spiral around my part. So now I like to break this kind of stuff up into at least 2 arcs. So I'm doing a 180 degree arc rotation, and then I'm going to do 180 degrees back. You could do 90, that's fine. Some controls have a little bit of trouble dealing with 180 degree arc. So certainly you could break this up into 4. That's okay. So since I'm doing 2 arcs, keep in mind, I'm obviously going to tell my X and my Y the end point of the first arc. So that's going to end over at 9 o'clock, 180 degrees out. Now my Z in feed, remember that's your chip load, but I don't want to go the full 5 thou because I've only gone half the distance. So I'm just taking my in feed and dividing it by 2. So 2.5 thou per ½ a rev. And this is where the spindle comes in. So I'm able to incorporate the spindle axis on my G2 move. Now in the Cinemeric control, I have the ability of adding this ACP or ACN command, and that just allows me to control my direction, positive or negative. I want to go positive direction, so I'm using an ACP command of 180 degrees. that's going to position it back. Now I could have just told it SP1 equals 180. However, that doesn't give me full control over the direction. So in this machine, it was actually rotating the tool backwards. So by adopting the ACP command, I was able to control the direction in the correct orientation. Then I give it the radius of the part. So that's my CR equals. So just like I was doing any G2 command with an endpoint and a radius. Next line brings me back. So I end back at 3 o'clock. And then I loop it. So it's a matter of, in my case, I created a couple labels and I looped it by the number of revs, spiraling all the way down. Now what I want to keep in mind here is my revolutions is going to start from wherever I started my Z. So here, if you notice, I was 50 thou up. So I'm not going to actually end with 50 thou or half an inch in depth. I'm going to end at negative 450. So I do need to take that into account when I'm doing my math, because I treated the Z as an incremental value. Because if you think about the spiral that I'm doing, the Z itself is the only value that's going to be at a new location every single time it spirals down. So if you treat it as incremental, then I can just do that corkscrew spin. Once we plugged all that in, really it's a matter of just coming over and running it. Let's jump over to give you a nice little close-up view. Now we're going to take some chips, get my safeties on. It's not going to be much of a chip, but a little bit. I want you to see specifically how the chip forms and how you can see that it's starting to mimic that turning scenario. Now, certainly I would have to, think about how much load I can put on the spindle. Right now we're going to be taking a pretty light load. She's just getting down into the part now. We should see it start to grab a chip. There you go. Starting to roll or form the chip, just like I would see if I was running it on a lathe, because it's really the same exact application for sure. Now, my position or my true concentricity of my hull, definitely going to be directly proportional to the speed and the rigidity of my machine. As you can see, we can certainly do it on this type of machine, but let's face it, this type of application really lends itself well to some big, large horizontal boring mill with a 50 taper spindle. But even if I'm on an application like a smaller 3-axis mill, certainly there's plenty of cases where this would be really handy to be able to apply. I was pleasantly surprised when I first put this machine into cut. This is a great little machine, but let's face it, I have a modest studio, so I was looking for a smaller machine to really demonstrate the applications more than do performance cutting. But this machine, actually, I've taken some pretty substantial cuts with it, and it took quite well, for sure. Now in this case, obviously we're doing a light chip load. I wanted to do it dry, so you can really kind of get in there and see the chip form. Certainly we're going to cut a little later. We'll put some coolant on it. I would definitely want to run coolant on a scenario like this if I was machining it. And if this was going to be a finish bore and I was trying to hold a real tight concentricity, I would probably go at a little slower speed. Certainly the cons here, this is not the fastest of machining processes, and you do have to watch your tool pressure, but if it's an application where I just don't have an opportunity of machining it otherwise, then might as well go this direction. All right, so just about finished up here. So now you can kind of visualize the toolpath strategy and start to hopefully see how this could be mimicked really on any type of machine tool. Certainly I don't think I would go longhand programming this at the control for all kinds of geometries. Doing it in this method really lends itself to straight bores or OD or ID, but when I get to tapers and stuff like that, it might be a little challenging. But if you look back in here, let's jump back in it real quick. You might get a chance to see it, but it's actually quite a nice surface finish. I threw an indicator in it before, and I was actually holding better than half a thou on that bore, which I was pretty happy with, especially on a 3.5-inch bore. And as far as depth projection, obviously I could keep going right down to the bottom of this. Nothing's going to change as far as my tool pressure because it's all the same. So I should be able to maintain a nice consistent bore all the way through. So from there, what if I want to get into something a little bit more elaborate, let's say? So we've also incorporated the ability of adding a cycle to this, and we call that cycle 959. Now, it isn't a standard cycle within the Siemens control. It would be an added cycle. So what I would say is you're not going to find it out of the box on the Siemens control. You can't even just turn a license on. The cycle would have to be brought in and set up in the control. We are going to show you the cycle right now. So if it's something that you guys are interested in, I would say reach out to the machine tool OEM first. Let's make sure that they're supporting that type of cycle in the machine. If they're not using it, or maybe you are an OEM and you would like to look at incorporating it, from there, certainly reach out to your Siemens rep and we can help you guys commission that up and get that running in your control. So let's take a look at cycle 959 in action. So I created a nice little part program here using our new added cycle. So the cycle itself is going to be found under various. If I expand my vertical soft keys, I'm going to get a new button called Interpolation Turning. Now, one of the first things you're going to notice is there's an option on the top of the screen with milling tool or with turning tool. When you do this setup on this cycle, it also adds a whole bunch of new tools to the machine's library. What it does is it turns on all of the turning tools. So if I go to my tool list and let's say we come down to create a new tool, I now have a new button called Turning Tools. Now the reason why we do this is because now the cycle can actually compensate for the geometry of this turning tool, specifically the tool nose radius, because this cycle is going to allow me to do tapers, chamfers, radiuses. It gives me a lot more power or capability within the routine. Now when I go to set up the job, it's going to be a little bit different. I'm not just going to choose a standard boring bar. So what I did was with my boring bar, I created two different cutting edges. So I have D2 and D3 as you see displayed on the screen. And now I still am using my length in my Z of 5.7019, but instead of having to shift my X by plugging the value in the diameter of the tool, I now can plug in the X value in the X field because I now have an X field available. And the radius over here becomes the actual true tool nose radius of the cutter. I have the rest of the geometry I would normally set up for a lathe. Now in my case, why I created a D3 is for OD or ID applications. I wanted to have two different offsets, right? Because if I'm in the ID, my spindle is shifted to the left, but if I'm on the OD, my spindle is shifted to the right. So there allowed me just two separate offsets. When I get back to the program, now what I did was I just set up a quick little job. I made a little selection here to jump between face, turn, bore, or boring with an end mill. And this is where I really can start to see the power of this cycle. So I'm not limited to just simple geometry. So in this case, let's say we're going to go into the turn, which is what we're going to cut right now. So I can use this for turning or facing. I can use it ID, I use it OD. Now the cycle itself is set up like I normally would see in the other Siemens cycles. So I have a safety distance and a retract value. Retract's going to be where do I go when I'm done. Safety distance is going to be how close do I get before I start feeding. From there, my feed per rev is going to be my distance, right? That's going to be my chip load. So just like before here, I got a little heavier chip load, 10 thou per rev. Now this is really cool. Inside the cycle, instead of programming standard inches per minute, I'm actually programming the surface feed. So the cycle is calculating based at the diameter I'm working out what the actual feed rate would be. So that's not 30 inches a minute, that's 30 surface feet. So when you see it's going to be running a lot quicker. And instead of relying on whether or not this machine had the ability of defining an offset in the work coordinate for the spindle, here we're doing it right at the cycle level. So I just tell it the base orientation of my S-pause, so I'm adding that 62.5 degrees I figured out earlier to my 0 location. Or in this case, since I want to be on the outside of the part, I'm going to be clocked around, so I just added an extra 180 degrees to that 62.5. We can go into rough or finish. So if I want to take multiple cuts, you can define OD, ID, back turn, a whole bunch of different scenarios. So we're going to be in OD. I'm going to do longitudinal or face turning. And then I come down and I define the geometry. So where's the center of the part? In my case, I chose 0 to be the center. What is the starting diameter? What's my ending diameter? So let's say we'll take 4.9, take a little cut at it. We're going to go 1/2 inch deep. I have a couple different strategies or options to tell it the geometry angles. What are my included angles? And this is what I really liked about it. The fact that I can then add my blending chamfers and radiuses. So you can toggle between radiuses or chamfers in all 3 corners. So if you've ever programmed one of our lathes, you would notice this cycle looks very similar to our turning cycle in the lathes. It does basically just about the same thing. So I define chamfer radius strategies. From there, select OK, and it builds the cycle. So I am doing the op turning cycle. So we are now set up for op 2 turning. Good. So we can close it up and take a cut on the outside, and you'll get to see it add a chamfer to this geometry. So let me jump over to a better angle for you guys now you've seen the program. So now at this point, you notice I'm going on the outside. Now I am taking more of a chip load, so I do want to have some coolant on this. And you see how far over I'm starting, because that's going to be how it comes down and achieves that chamfer. So at first it looks like it's going to take a huge chip load, but as it starts to come down, it's following that slope. So the system, the cycle, is actually now creating a spiral that's progressively getting larger and larger. Had I been doing a taper on the outside, it would have done the same. We should be down on it just a second here. We'll be getting a chip load. Now in this scenario, I am using flood coolant. You do want to get some pretty good lubricity on this. This is 6061, so it tends to get a little gummy. I actually recently just switched over to the Motorex Swiss Cool 3000. Very, very happy with it, to be honest with you. I've been searching for a good coolant here. I wanted certainly something with some real good lubricity, but you know, a lot of the coolants have a tendency to stain or pit your machine. Obviously I do a lot of videos here, so I want this machine to stay really good looking. In this case, I haven't had any staining. And to be honest, it's kind of funny, one of my biggest factors for picking my coolant was smell. You can see I'm in kind of a modest studio here, so I wanted to make sure that it wasn't going to smell, and I almost don't even notice any smell from the coolant. If you notice anything, it's probably a little bit of a mild sweet smell. But anyway, so that's just a product that I just started using. But here you can start to see the cycle in action. So with that being said, we're coming up on the hour. Lars, do we have any questions from the audience?
No, not so far. We had a couple comments. I guess there was a little bit of a blur for sound quality and recording, but that has been resolved. So looks like we're all clear on my end here.
Perfect. Well, if you guys have any questions, feel free to certainly reach out and talk to us and ask us some questions about it. I hope you found this informative, and if you enjoy these video segments, please make sure you like them, share them, and follow the channel. This way you'll be able to get any updates for what's coming up next. And let me just say again, thank you for spending your time with me, and stay safe and healthy. And I look forward to seeing you guys again real soon. So have a great day, and thank you, Lars.
Hey, no problem, anytime.
All right, bye-bye.